Already on?
You got 75 lakhs.
Switch on.
It's on.
On? Okay, welcome everybody to this afternoon's session. Our first speaker is Anupam Kundu from ICTS Bangalore.
Okay. Can you hear me? Yes. Okay, so let me first thank Sanjeev and Manju for organizing this very nice conference. It's a wonderful conference. And also, RRI is also a special place for me. I did my PhD from here, like 13 years back. 13 years back. And it's nice to give a talk in this auditorium. Okay, so I'll talk about some results on collection of hard rods. So this is, the preprint is this, and this work is done in collaboration with these people. Sahil is a graduate student at ICTS, and Abhishek Herbert, they are also here. And Minal is a master student who has recently started working on some problems on hard rods. Okay, so let me start with generic non-integrable systems. So this generic many particle systems with typical initial conditions eventually thermalize to Gibbs state, which is characterized by a few conservation laws: mass, energy, momentum. And such systems typically have good dynamical properties such as chaos, mixing, and ergodicity. And the evolution of these systems on macroscopic scale to that homogeneous stationary state can be described by hydrodynamic equations, which are few, which has also Navier-Stokes Fourier types of dissipation terms. So for an one-dimensional fluid, here I write the hydrodynamic equations. These are written in terms of three independent fields: density, momentum, and temperature or internal energy. So the red terms are dissipative terms. These are Navier-Stokes terms. Without that, the rest of the terms correspond to Euler equations. And the connections to microscopics are through this internal energy and the pressure, which comes from the equilibrium statistical physics. That actually gives this pressure term here. Okay, so this is a kind of a description that actually is valid for non-integrable systems, but the scenario is different for integrable systems, where you have extensive number of local conservation laws, and such systems, they fail to thermalize to Gibbs state. And it is believed that such systems with local conservation laws thermalize to, I should not say thermalize, but I mean goes to equilibrate to generalized Gibbs state upon coarse graining. And also the approach to such a homogeneous generalized Gibbs state is given by generalized hydrodynamics. And what is generalized in this system? Let me briefly tell in 2 slides. Herbert has already talked about such concepts for Calogero system, Calogero fluid. So this is a picture that I have taken from Benjamin Doyne's lecture note, which summarizes this very nicely. So the generalization is for non-integral systems you have finite number of conservation laws, and for integral systems you have infinite number of conservation laws, and which are local. And such systems goes to in after very long time, it goes to stationary homogeneous stationary states. In this case, it is described by this kind of Gibbs ensembles, which are characterized by these few conservation laws and the corresponding chemical potentials. Whereas in this case, you have to consider all the conserved quantities with the same number of chemical potentials. And the approach to this station state at late times, when the system is more or less kind of slowly varying over space and time, is described by hydrodynamic equations. And here you write down hydrodynamic equation corresponding to these slow variables. These are conserved quantities. So you have corresponding densities which are varying slowly. And you write down hydrodynamic equations, assuming that locally you have a local equilibrium kind of description. Similarly, here you also have, you assume that there is a local kind of Gibbs, generalized Gibbs type of description, and then you write local, hydrodynamic equation for the local conserved quantities, and also you have to write for all of them. So you have extensive number of such equations. These are basically coming from the continuity equations. Okay, so these are some examples of classical particle systems which are integrable. This is Toda model, which are particles in one dimension interacting via exponential interaction with in the separation between successive particles. Hard rods, of course, they cannot come closer than a distance a. Colloidal fluid, which Harvard has talked about in detail. And there are many other models, quantum models as well as continuous models. But hydrodynamics, let me first tell you what is this, and then I'll tell you about how to get this, not derive, but briefly argue how to get this for hard rod systems. So for integral systems, hydrodynamics is written in terms of the phase space density, quote unquote phase space density of quasi-particles. So what are quasi-particles? So in integral systems, the multi-particle scatterings are actually composed of well-separated two-particle scattering. And as a result, if you have particles, let's say from very far from scattering regions with some well-defined momenta, like here, let's say you have two particles which are at very far from the scattering region with two momenta, they scatter and they come out with the same set of momenta. If these two particles did not interact, it would have come like this, and after that it actually comes like this, but it has the same momenta as this. So here in this system, for almost all time, you will find always a particle which is following this given set of momenta that you had at very, very far past. So quasi-particle is basically a tracer that you attach on real particles that actually jumps from one particle to another, in such a way that it actually follows a given momenta for almost all time. And so the evolution of these integral systems can be thought of in the large n limit as collection of these quasi-particles, and you can think of densities of these quasi-particles. So let me explain this. It is easy to understand in the hard rod system. So let's say you have two hard rods, they come and they collide, and at collision they exchange their momenta, and this guy gets the moment of this guy, and this guy gets the moment of this guy. But you can change the color also, and you can think of that this is actually a quasi-particle and this is also another quasi-particle. Okay. Okay, so here I would like to mention that in the whole talk I will consider the masses of the particles to be unit, and so I will use the notation P and V interchangeably for the momenta and velocity. Okay, so you can write down a hydrodynamic equation for this phase space density, and it looks like this. I'll explain different terms later, but you also have seen this kind of expressions in Harvard's talk. Harvard wrote rho, but I am writing F. And this is similar to, like, this equation looks similar to like Liouville equation of streaming of non-interacting particles. It's similar. Only thing is that this is different, and I'll explain that. But usually we write hydrodynamic equation in terms of the conserved local densities. Like this, in this case, you have to write infinite. And I'm saying this set of equations are actually contained in this. You can easily get. So conserved quantities for integral systems are actually functions of this asymptotic momenta, which remains conserved even after scattering. They come and then they scatter and then they go. The set of momenta remains exactly same as their initial momenta. So the conserved quantities are basically functions of those momenta. And you can write down, find out the average of this quantity in terms of these densities, and you can identify a local density of this conserved quantity and corresponding current, and you can see that this equation actually will give you this. So you have both a kind of equivalent description. But why are people interested in this kind of hydrodynamics for integrable system? It's actually people got interested. The interest came from some results or observations that people have made for trapped integrable systems. So there are experiments. So this is one famous experiment in which the authors actually have created one-dimensional array where they have confined 1D Bose gas, which is basically some rubidium atoms, and they created two blobs separated and then created them into opposite momentum states, and then they release it. So, and then look at the density through absorption microscopy, and then they see this. This is a cartoon of the evolution, and this is actually the observation. So they see that these two blobs come, merge, and then again separate, again merge, and this happens. This oscillation happens for a very, very long time. Many such oscillations, even thousands of such oscillations. Even after that, it does not thermalize, even though the system in this trap is not strictly integrable. So how to understand that? And the understanding came from the development of generalized hydrodynamics, which got developed from these two papers, which actually is basically writing down equations for phase space densities of the quasi-particles. But to understand the experiment, you have to modify it a little bit. You have to add an effect of the trap, term from the trap. But such equations also have many hydrodynamic conserved quantities, and this from this one can explain the behavior observed in that experiment. Not only that, there are other experiments which actually have made direct, actually have tested direct predictions. So this density they have measured directly and compared with the theory, and they have verified this experimentally directly. So these are like quantum systems in trap, but there are also studies in which you have classical systems which are also in trap, and there are studies, and it also shows a very slow thermalization. For example, there are lots of hard rods in harmonic trap, and then look at the possibility of thermalization, and and these authors have observed that if you look at the density here at the center, it actually has oscillations for a very long time, and it doesn't thermalize. But if you look at if you look at the phase space density then of these rods, it actually keeps on developing finer and finer structures at very large times. If things thermalize, you will not see such finer structures. You will see kind of diffused, smeared out phase space density, but here you see that it actually creates lots of finer and finer structure, which actually is a signature that it actually is not thermalizing. Okay, so these are the kind of motivations for studying generalized hydrodynamics. We also have done a similar study, and this is a preprint, but I will not go into this study today. Okay, so in this talk I will consider hard rods in one dimension, no trap, in a box, and this is the Hamiltonian, and the conserved quantities are basically moments of the velocities of the momenta. So these are for each alpha you have a conserved quantity, because they collide and they exchange momenta, so momenta do not change, the set of momenta remains the same, so all moments of the momenta remains same, conserved. Okay, so what do we study? We take this system and we prepare this system in non-equilibrium, initially in a non-equilibrium state, which is a low entropy state, and see how does it evolve, and compare it with the solutions of the hydrodynamics, and see if they approach stationary state. This is one thing that we want to see, and we also want to understand and demonstrate the effect of dissipation in this system. Okay, so before going into that, let me give you a microscopic description. So these are the kind of sample trajectories the hard rods you can simulate, and they look like this. But if the radius of the rods goes to 0, then they become hard point particles, and the corresponding trajectories look like this. They just get reflected off each other, and they exchange momentum. Now, you can actually have a nice transformation from any hard rod microscopic configuration to a point particle configuration. The transformation is the following: that for any these configurations, you just remove all the inaccessible spaces between successive hard rods, and you get a configuration. The prime configurations are point particle and the unprimed are rod configurations. Of course, the velocities do not change, but the positions change and the box size also becomes smaller. Now, once you have such a configuration, then you can do this at each time. Not only that, you can you evolve this configuration to till some time t. You can evolve this configuration till some time t, and you see that these two configurations also are the same mapping. So the dynamics actually maps. So from a hard rod configuration, initially you go to a hard point configuration, you evolve and then come back, and that's how you can get a configuration of the hard rods. Actually, this was the mapping that was first introduced by Parkas, Joel Lebowitz and Peter Sykes, and long back.
In this case, the tracer particles will not have an encryption.
I'll talk about one such configuration. Okay. So by doing this, just a demonstration. So you map this. These are the trajectories of the hard point particles, and you can directly simulate these are the trajectories of the hard rods. But you should be able to, by doing this mapping, you should be able to get these trajectories from these trajectories, and indeed you get. You can see that you get exactly those trajectories. So dynamics actually maps. Okay, so we use this mapping, and using this mapping we can compute few things microscopically. Let's say the density of the rods for any finite n, and using this mapping one can show that the density of the rods can be written in terms of some probabilities of the point particles, which are basically this is the probability that the ith point particle is within z2 z plus dz. And this quantity you can compute for some specific initial conditions, of course. For some other initial conditions also you may be able to compute. We did this, and one can see that it actually works very well, even for any finite number of rods. So this is the initial condition for point particles. So we take the point, put the point particles initially in the some fraction of the box uniformly, and the corresponding density in the hard rod is look like this. And then we let them evolve. It evolves, and we see that the description, theory and simulation is very nicely matching. And not only that, it actually tries to fill up the full box. It's like initially the hard rods are like half of the system, and it tries to fill up the full system. And if you do it for a very last time, it will become almost uniform. Okay. Sorry? Here I am doing microscopic calculations. I'll talk about quasi-particle again. Not only this is a calculation in a box. Okay, I should mention that these are the calculations that is done recently by Meenal. And also you can do it on a line from some other initial condition. This is Gaussian, and the corresponding initial condition for the rods are this, and then you evolve, and you see the formula works pretty well. Not only that, you can also compute the joint probability, which is like 2-point correlation, and this also you can compute. We have an explicit, this is big formula, so I didn't write it. I have an explicit analytical expression, and it also works for any number of particles. Here I show a comparison for n equal to 5, and it works pretty well. Okay, but we are interested in hydrodynamic solutions. So these are kind of solutions for finite any number of n. So we want to find out the solution in the n going to infinity limit. And in fact, actually you can take a large n saddle point limit of these expressions, and you see that it actually is given by in this form. Rho point is the density of the point particles, and this is the density of rods. Of course, they are in a different space with different coordinates, and this is different coordinates, and the coordinates are related by this. F is cumulative density of the point particle density. And we will see that this is indeed a solution of the Euler hydrodynamic equation for hard rods. I will show that. Okay, so what is the hydrodynamics for hard rods? Recall that the hydrodynamics of hard rods are written in terms of the phase space density of quasi-particles, and in this case for the hard rods, the label exchange rods are quasi-particles. At each collision you just exchange the labels, and then the rods that you get, these are quasi-particles. Okay, and these we want to write down the hydrodynamics in terms of the densities, phase space densities of these quasi-particles. Does that answer your question? Yeah. Okay, so before that, let me tell you what is the generalized hydrodynamics for point particles when the radius is 0. So when the radius is 0, when these are point particles, hard point particles, they come and they reflect from each other and they exchange their velocity, but at the same position. And at that position, you can exchange the labels, and then they become non-interacting particles, non-interacting ballistic particles. And for that thing, it's very easy to write down the evolution of the phase space density. So suppose we denote the phase space density of point particles by F naught. So I'm putting a naught for denoting densities for point particles. And this is the Liouville equation, which is very easy to see. And here you have the velocity, because you want to find out the density of point particles at velocity v. For hard rods, this equation gets modified, and instead of v, you get an effective velocity. Why? You see that, so suppose these are the quasi-particles, and you want to write down the densities of this. And you see that after the collision, this guy got an extra displacement. If these two did not collide, they did not see each other, it would have come here. But because of the collision, it got an extra displacement. Similarly, this one also, it would have come here, but because of the collision, it got an extra displacement. And so that means that its velocity, it was going with velocity v, but its actual effective velocity cannot be just v. It has to modify, has to get modified. So this can be easily seen from this picture, or you have many hard rods. So let's say this is the quasi-particle. So this let's focus on this quasi-particle. It collides, and the red color changes from one particle to another particle because I am following a particle with a given momentum. But the actual particle is this, the magenta color, but the red particle is the quasi-particle. If this particle, this rod did not see other particles, it would have come here. But because of the collisions with many other particles, it actually has come here. So it has an extra displacement. So its velocity cannot be just v. It gets modified. Yes.
So the advantage of using these quasi-particles is that the momenta is, you keep the same momenta, or I mean, why do you use these quasi-particles in the first place? I mean in this description, why are they necessary? Why do you need quasi-particles?
Because these are the particles which have, so basically I want to identify particles with given momenta.
Okay.
Because that's how, that is the thing that I can write down a density for.
Okay. And so
and those are I'm calling them quasi-particles.
Exactly.
Yeah.
So I mean, it's just different particles. The identity is not.
Yeah.
But it's just the same momentum.
Yeah, it's just the same momentum. So you just identify particle with given momenta.
Okay.
It could be different particles of the initial levels.
Okay. Thanks.
Yeah. Okay. So of course you can derive this effective velocity more rigorously. Here this is the density, this is the marginal of the phase space density, and this is the fluid fluid velocity field. Okay. So similar picture you can see from other integral models also for Toda fluid. So this is a picture that I have taken from Herbert's paper. Also this one also I have taken from Herbert's paper. This is the again a quasi-particle. Basically you are trying to follow a particle with a given momentum, and this is actually the actual particle. But you see that it would have come here if it did not interact with other, but because of the interaction it actually has reached here. So you see the similar thing, and from this picture also you see that there is an extra displacement. Now this extra displacement is dependent on the what kind of interaction Hamiltonian that you are choosing for the integrable system. And this is called the phase shift, which is related to the scattering shift that Herbert was talking about. Okay, so in general, this V effective satisfies this equation which Herbert also wrote, and you can easily, I mean, intuitively understand. So this is the bare velocity of the particle, but it actually gets an extra contribution from the collisions. So the contribution is this. So this is the displacement at each collision between two particles of bare velocities. Yeah, I messed up the notations. This should be P, or all of them should be V. So this is the kind of a extra displacement that two particles of momenta P and P prime gets. but this is the rate at which they collide. This is the relative velocity at which they collide. And this is the density of the particles at that moment. So this is the number of particles that are colliding, and at each collision there is this much amount of displacement per unit time. So that should contribute to the velocity, and that's, this is the equation that satisfies the effective velocity equation. You have to solve this. So for hard rod, this phase shift function is very simple. It's just minus a, because at each collision they get shifted by a. Okay. And if you use that and put it here, you can show that it is actually the effective velocity is this. But you can derive this thing from a more simpler and intuitive calculus. Actually, Parkhurst did it long back from a kinetic theory perspective. Okay, so this is the full hydrodynamics, Euler hydrodynamics of hard rod fluid, and everything is specified. But you can also add Navier-Stokes term to it. I will not say how it was derived, but this is the expression of the Navier-Stokes terms, and this was done by Herbert and Benjamin through a Green-Kubo calculation. And then later, not later, before that, Boldirgini and Schwab actually has done more rigorously and shown similar same Navier-Stokes terms. Then recently, Benjamin and Jacopo and Denis Barner, they have computed such Navier-Stokes terms for other integrable models, more general integrable models, such Navier-Stokes terms. Okay, so this is the generalized hydrodynamics till diffusive corrections. Okay. Okay, so once again, I would like to remind you that this is the things that I want to finally study, the evolution of non-equilibrium initial state, and see if they approach GG, and what kind of initial states can approach GG. Are there initial states which may not, which will not approach GG, and also understand the effect of this Navier-Stokes terms in this evolution. Okay, and yeah.
Can you, to the Euler equations, so you said ansatz at some point, and I didn't understand why, why is it an ansatz? Is it an approximate?
It's just you make an intuitive explanation, but I don't think there is a rigorous proof of this for a generic system. I think for Toda fluid, Harvard has a paper in which you can show this, but maybe you can make a comment.
So I'm responsible for the ansatz. Okay. So you see, the way you do the argument and the way Anupam showed us to do it, you sort of argue with isolated collisions between quasi-particles, right? And so when you look at this formula, I mean, you might be a little bit suspicious in the sense that, you see, this formula is supposed to be true for any density. And so when you look at this formula, I mean, then you might think, it's more like an ansatz. I mean, the argument might not fit completely, right? And so now, of course, we have other ways of deriving the formula. And in fact, this formula was derived for soliton gases already in the early 2003, also with a very different argument. But eventually, it boils down to this equation, right? And so this equation seems to be sort of, valid at great generality. And in some sense, one say that, for many systems, we have verified the ansatz.
Okay. So what do? We actually get the solutions of the GHD equation and also do simulation by doing evolving microscopic dynamics and compare. And once again, for that, we use this mapping that I have talked about. But apparently, to find out the solutions of the hydrodynamic equation, also we use the mapping. And that mapping actually for hydrodynamic quantities gets translated into these equations. So this mapping becomes this. It's actually basically, you can write down x prime is equal x equal to x prime plus this. This is basically the number of particles below the ith particle. So it's actually say this is exactly that x prime. There is a point particle, and this is the number of particles below x prime. And for each particle you have to add extra distance a. So and that's how you get the rod corresponding to this point particle. So this is the transformation, and the density also has a similar transformation. You can actually show that this the density will have this transformation. If you use this transformation, so the coordinates transform this way, and the functions transform this way. If you use this, then the Euler GHD of hard rods actually transforms very simply to Euler GHD of hard point particles, and you see that here this becomes just V, not V effective. Okay, which you see for point in the microscopic dynamics also, and which now this equation is very easy to solve. You can solve it, and then you can transform back, and that's how you can solve the GHD equations, Euler equations for hard rods. So what we want to investigate is whether, starting from some initial non-equilibrium state, whether it will reach a homogeneous Hessian state. Of course, the velocity distribution, the marginal velocity distribution will not change because the velocities are not changing. So it will never change. So we want to initially create a density profile which is not homogeneous, and at last time we want to see whether it will go to a homogeneous density profile or not. That is the simplest thing that we can check, whether the system reaches a GG state, because in a GG state which is finally homogeneous, and so the density profile should be homogeneous. So that is what we want to check, and also we want to check if there is spreading in the density profile to check the effect of the Navier-Stokes terms, and that we do for 3 different initial conditions. Okay, so let me talk about the first initial condition. So the in this case we have rods which are uniformly filled, but the velocity distribution is inhomogeneous. In the left half of the box, all the rods have velocity 1, whereas in the right half of the box, all the velocities of the rods are chosen from Maxwell distribution. So initially, the phase space distribution has 2 components: one for the special rods of velocity 1. That's why you have a delta function in the velocity distribution, and on the right side you have Maxwell distribution. But especially the rods are uniformly filled with density rho, and we want to see how does it evolve. This density profile will evolve. So initially it had 2 components. We see that at later time also it will have 2 components, because the special rods will be there, because there will be say same number of rods with velocity 1. So this there will be 2 components always. Only thing is that the density was rho, now it will be some other density profile. And similarly the background density profile will be phase space distribution will be like some other function. And the marginal of that will give you the density profile. So we compute rho G and rho B and plot. So initially the special rods are in the left half of the box, and the background rods are in the right half of the box. And it evolves with time, and these rods actually starts moving this way, and you see, and this sock actually moves in the right direction. It gets reflected and comes back like this, and this also goes. Here the dashed lines are simulation, whereas the solid lines are solutions of the Euler equation. This is from the background rods. This thing comes, and these rods actually enter into the background rods, so that's why the sock size becomes smaller and you get a spread, and then it again gets reflected and it comes like this. But you see that the Euler solution and the simulation matches quite well, but if you look closely near the sock, there are some discrepancies. Dashes are simulation, and these lines are like very sharp discontinuities. So this mismatch or the discrepancies are coming from the Navier-Stokes terms. Okay, so let us try to investigate that. So we look at this near the sock, the profiles near the sock for a small time. in the early times of the evolution. So these are the profiles near the shock. We have actually bring them at the same place. So basically shifted them at different times so that they are at the same position. And you see that with time they spread, and the spreading increases of the shock. It spreads, it widens, and the spreading increases with time, and it increases as a square root t. If you scale the x-axis by this, all this curve actually collapse onto the same curve at small times. You have a question, Martin? Okay. Okay, good. But you can understand this easily. So the microscopic origin of this spreading is the following. See, this for a given initial configuration, let's say all the positions are fixed and the momenta. This is for single initial configuration. If you look at evolve this, then if you look at the density profile of the special dots, then there will be a sharp shock. So for a given configuration, there is a sharp shock, but the position of the shock depends on changes from one initial configuration to another initial configuration. Why? This moves because of they are moving, as well as they collide with the background dots. Okay. And then, so the position actually fluctuates because the number of background dots they encounter, the shock encounters, is actually changing from one initial configuration to another initial configuration. And the initial configurations are random, corresponding to a given macroscopic state. So this thing fluctuates, and that fluctuation is basically the number is proportional to the number of fluctuation in the number of rods that this shock profile has encountered, or the number of background dots has gone past the shock profile of the special dots. And you can, so in time period t, this shock has moved over of a distance of order t, and in that distance the number of background dots, actually the fluctuation can be obtained, and it's actually proportional to the square root of the mean, because initially they are put uniformly as a Poisson distribution. So in later time also there will be Poisson distribution, and the mean of such particles, number of such particles over a distance t, will also be proportional to t. So that's how we can explain this square root t behavior. But this spreading of square root t does not continue for a long time. After some time the rods see that there is boundary, they get reflected, and this background dots hits the boundaries and comes and back. As a result, the fluctuations of the rods that they have encountered, that have entered into the region of the special dots, actually got correlated, and so this spreading stops. Okay, so this profile, initially it was half of this thing, it actually broadens, as well as this shock spreads, but at some time it stops. So these are the profiles at later time, and you see that at later time this profile actually moves like a rigid profile with some constant velocity, and the spreading, if you bring them together, there is no scaling, and they just match with each other for a given system size. And but the saturation of the spreading, the saturated value of the spread of the shock, depends on the size of the system. This is the late time saturation for different system size, and you see that saturation actually scales as square root n. So the saturation spreading, saturated spread is of order root n, whereas the full system size is order n. And this full density profile moves as if a rigid structure is moving with a constant velocity. So the total density will be like this. This was the initial density. These are the special dots. These are the background dots. And at very late time, the total density becomes this. The background dots, they have gone spread to the full system. That's why their density, overall density, has gone down. And these special dots have broadened. That's why their density has come down. But this does not broaden again further, and also does not spread further. And such a structure moves like this, and keeps on moving it. So as a result, this density never goes to a homogeneous state, and such initial state never goes to a GG state. So if you start from some initial configuration, this from this initial configuration, this system does not go to a GG state even at very, very long times. Okay, so but ideally one should be able to get this full profile of the spread from the Navier-Stokes equation. Yes.
So once you map to this point particle, then the left system and right system effectively independent, right? You can evolve
In the point particle.
point particle picture, right?
But the transformation is after you do the transformation, then it becomes this. So in the point particle picture also you will have this thing which moves, but it does not spread. But when you do transform, then it spreads, as well as this will also have. For point particles, you will not have this spreading also. Okay. So we cannot do solve this equation, Navier-Stokes equations at least till now. So we look at a different initial condition, and this is a condition that Tidib was asking. So we fill the box uniformly, except and the velocities are chosen from in Maxwell distribution, but except that there is a special particle at 0, and we want to ask what is the probability of finding this particle at some position x at time t. So this is like a tracer particle, and what is the answer? So if first let us consider this simpler case. If there are point particles, what would be? If the point particles, it actually effectively does not see, because it just collides and then you just exchange the label. So in time t, it just moves by distance v0 t. So initially it was distribution was delta x, then at time t it will be a shifted delta function. Now if you want to find the solution for rods in the Euler GHD, in the Euler GHD it actually moves again with another velocity which is effective velocity, and in this case it is constant because the background is uniform and it doesn't have any velocity field. So again it will be just be a shifted delta function, but at a different place. But if you do a simulation, you will see that it actually not only moves, so I have shifted them, but it also spreads. And that spreading comes from the Navier-Stokes term. And you see that this spreading is actually has a scaling of square root t. It has a square root scaling. And we find the scaling function explicitly by solving this equation. And one can solve this equation and find that this is a Gaussian with the width is given explicitly in terms of the initial velocity distribution explicitly. So this is what we obtained from solving this equation, but this was also obtained by these people from microscopic calculation. Okay, so at least for this initial configuration, we can actually solve the Navier-Stokes equation. Okay, good. So now let me talk about the last initial condition. So this is the initial condition for which it actually goes to GG state. It is actually the free expansion initial condition, where initially we put all the rods in the left half of the box and the velocities are Maxwell distribution, and we let them evolve. So this is the phase space evolution of the rods. They evolve like this, and at late time they create this kind of fine structures. This is similar to hard point gas, equal mass, and they also develop a lot of fine structures. But in contrast, if the masses of the particles are different, then you see that after a short time they just fills the full system. You can visibly see that it actually thermalizes. But here you have a similar structure, so they do not thermalize to the usual Gibbs state, but they go to equilibrate to generalized Gibbs state. So in this case, we compute the density evolution, and we see that the density initially was like this, and it evolves and goes to a flat profile. Similarly, the momentum profile was initially like this 0, and then it evolves and finally comes to a 0 profile. And we have explicit expressions of this. Actually, we have explicit expression for all the initial conditions. I didn't just show the expressions, and it compares with the simulation very well. Okay, so this brings me to the conclusion of my talk. So I have shown you some microscopic solutions of the density and joint probability. And then I showed that in the large and limit, you can actually get some solutions forms which are solutions of the Euler GHD equations. And the Euler GHD solutions matches the simulation pretty well, except for small discrepancies that arise at the shocks. But to observe such discrepancies, you need to prepare initial conditions very specific way. You have to have a singular component in the velocity distribution, otherwise you will not be able to maintain the shock. Because unlike for Euler equations in non-integral systems, if you start from in naturally developed shocks, but here for hard rod case, they do not. So you have to create specific initial conditions which are like you have to have sharp velocity components in the velocity distribution. Okay, so yeah, okay, thank you.
Okay, are there any questions for Anupam?
Yeah.
Actually, it's a naive question. I wanted to know if you have these hard rods or hard disks in dimensions higher than 1, then also they don't thermalize in the potential?
In higher dimension, it's not an integrable system.
Yeah, so, but they'll thermalize?
In higher dimension, yeah.
Yeah.
Can you quantify which initial conditions lead to one or the other? Like, I mean,
That's what I said.
yeah. So if you have a sharp
You should have a singular component in the velocity distribution. For example,
with some extensive number of them or something like that.
no, the velocity distribution would be like you should have a delta function type velocity distribution. So there should be a macroscopic number of dots with same velocity.
Yeah. Okay. Yeah.
So that.
So I mean, if there was just one, it wouldn't make a difference. But it's a macroscopic number with.
Yeah, but one. I mean, you can one actually it keeps on spreading. You can say that okay, it doesn't thermalize, or in the thermodynamic limit you just ignore that, and the rest of the rods are actually thermalized. So
Right,
it
right.
actually is moving in a thermalized background.
Yeah. Okay. Okay. Thanks.
So initially you showed some plots of correlation functions, right, which you computed
Yeah.
from microscopics, I guess.
Yeah, it's a joint probability. I didn't compute the correlation. You can compute the correlation.
That was from complete microscopics, right?
Yeah, yeah.
Is that something also that using fluctuating GHD that can be computed? Like, is that what
Yeah,
Tomohiro?
so yeah, I should mention this. Recently, there is a macroscopic fluctuation theory, and they computed this kind of quantities. But that is their formula. I don't know. I didn't understand what is the explicit. They don't have an explicit formula, and I have a formula which I cannot evaluate for a very large n numerically. I am still struggling, but I get a large n saddle point form, which also I am not able to verify. I mean, this formula involves lot of factorials. It's numerically it's difficult. So. Yeah, but you have huge. Starling is also not working.
Okay, any more questions? Okay, if not, let's thank Anupam again. Okay, good. Okay, so our second speaker this afternoon is Kabir Ramola from TIFR Hyderabad. Kabir.
Thanks. I'd like to start by thanking the organizers, Sanjeev in particular, for the invitation, and congratulations to RRI on 75 years. And yeah, RRI, of course, hosted the first schools in statistical physics, which I was also part of. And so, yeah, it's really part of the development of many of our sort of research careers. It all started here in RRI, so, and in this room especially, so it's particularly nice for us to come back and give talks here. So today I'm going to talk about a question that has sort of emerged in the last few years on current fluctuations in interacting and non-interacting active particle systems. And this work has been done in collaboration with the graduate student Steffi Joes, who did most of the calculations, Rahul Dandekar, who was a postdoc in Saclay, and Alberto Rosso, who is here in the audience, as well as LPTMS. So active systems have become quite important in the last few years, where they are systems that can perform directed motion by self-propulsion, and there are a major class of non-equilibrium systems that are being investigated today, mainly because they break detailed balance at the local level, and because of that you can create many interesting non-equilibrium phases using these active particles. And so some interesting questions that we would like to study are, can fluctuations in such systems be studied analytically? What are the effects of initial conditions on the fluctuations in active particle systems? And one particular question that I will be focusing on today is what happens if you quench the initial bias directions of such systems? Does it lead to some different kinds of fluctuations? This is very similar to the question that Anupam was just talking about, where he quenched the initial directions of half the particles in his model. And then one other question that I would like to sort of touch upon is what happens near a motility-induced phase separation transition that active particle systems, especially in interacting active particle systems, display. So initially, this is the outline of my talk. Initially, I'll talk about a non-interacting active particle model, and I will calculate current fluctuations for different initial conditions, which I will then detail here in the second part of my talk. And then I will move on to an interacting active lattice gas model that has been studied in the literature over the last 4 or 5 years. And I will derive current fluctuations for this model and show how it connects in some limits to the non-interacting case. So let's start with the non-interacting active particle model. The model is very simple. This is a system that has been considered by many of the researchers in this audience today. And for simplicity, I will consider run and tumble particles that are described by the Langevin equation. The velocity of the particle is given by v times some telegraphic noise variable, which takes values plus or minus 1. And so this random variable sigma switches values with rate gamma. So it just basically either moves with a velocity plus v or a velocity minus v. And this is the simple run and tumble model that has been sort of studied quite a lot in the literature recently. So the question I will focus on is the following. I will start with particles on the left side of the origin. This is a step initial density condition. And then ask the question that if you put the particles in a certain order on the left side of the origin, what happens to the number of particles that emerge on the right-hand side. So this is very similar to the question that David Dean was talking about, a fusion of particles through the origin. But in this case, active particles have one additional degree of freedom, which I've sort of put here in some colors with plus or minus. So in the particle positions, x1, x2, x3, could be put at a particular point, x1, x2, x3, and so on. But they can also be started at different initial orientations. So if it started in orientation towards the left, I've colored it blue. If it started in the orientation to the right, I've colored it red. And these can be labeled by some variables m1, m2, m3, which is plus or minus 1. So this is in analogy to some magnetization variables. So you can have a density variable, which is rho, and a magnetization variable, which would be given by some m. So the question I will focus on is a fraction of particles that you start at the left of the origin in some in the plus state given by f plus, and some fraction of particles started in the left of the origin in the minus state, which I label as f minus. And then we look at the dynamics. So this is space and time. And so if you just start the dynamics of the system, you will see initially the particles that are oriented towards the left will initially perform motion to the left, and then they will flip with some randomness. And the question that we are focusing on is how many particles move from the left of the origin to the right at a given time t, and we want to understand the fluctuations of this quantity. Yes, please. Yes.
This initial state is not the stationary state.
No.
Is there a reason for you to choose this particular?
Yeah, so you could, for example, choose this from an ensemble of from the non-equilibrium steady state. That you can do. But you can also just completely quench these variables, and we want to understand what the effect would be if you can tune that. For example, as I think David was pointing out, as well as I think Gregory was pointing out, that you can choose any initial condition with some hyperuniformity of the positions, and you can tune the value of the fluctuations depending on what the initial condition. So that's what we are testing with an additional degree of freedom here, because these are active particles. So you have another degree of freedom which you can test. Any other question? Okay. So this is the question that we are considering for the non-interacting particle case. So the quantity that we are interested in is Q, which is the flux of particles across the origin up to a time t. which is the number of particles that cross the origin, or you could equivalently say the number of particles on the half-infinite line at a finite time t. We focus particularly on the role of initial conditions on these current fluctuations, starting from a step initial density profile, and very similar to the work done by Gregory, Satya, Alberto. We start with positions distributed uniformly in a box minus L to 0, and then we take the limit L going to infinity, N going to infinity, with the density kept fixed in our analytic calculations. And we consider the fraction of particles F plus, initialized in the plus state as I mentioned, and F minus initialized in the minus state. Okay, so we want to now look at the effect of initial conditions. So there are two very well-known kinds of averaging done when we look at these sort of particle systems. One of them is known as the annealed setting, where you average over the initial realizations consistent with some macroscopic property like the mean density rho. Another one is the quenched initial setting, where you keep the positions of the particles fixed and then you average over histories, but keeping the positions fixed. So this will have lower fluctuations because there is no fluctuation in the initial condition. So these two are the general sort of averages that people consider when you look at questions dealing with these current fluctuations. So just for ease of notation, I'll denote an average over the history of the trajectories conditioned on a fixed initial positions, which is xi, by this triangular bracket, and then you can average over the initial positions, which I'll denote by this over bar. So these are the two kinds of averages that you can do. So in the annealed setting, the generating function can be given by this average of this exponential, and I'll do an expansion and show you why this happens, over fixed initial conditions xi, and then average over positions xi. Similarly, in the quenched setting, in this case you have to do an average over the logarithm of this quantity and then take the average over the logarithm, which will give you the generating function. So just to illustrate this point, let's look at the annealed setting. In the annealed setting, you take an expansion of this quantity. So you have fixed initial conditions xi, and then you take an average over xi, and then you average over all initial conditions. So if you do an expansion, you'll see at first order you have the quantity q, which is averaged over both xi and the initial conditions or initial positions, and q squared will now be given by this average over all possible initial conditions and all histories. If you look at the cumulant generating function, you can see that the annealed average will have average over all positions and all histories, and if you look at the fluctuations, you now individually look at the q squared average over histories and positions, and similarly you look at q average over histories and position, and then you subtract the square. This is in contrast to what you would do in the quenched setting. In the quenched setting, you fix the position of the particles and allow all possible histories to occur, and then you calculate the cumulants for that particular realization of x. So if we were to do such a thing, it turns out that the first moment will be the same, exactly the same as this, but now you look at this, this quantity, which has a different kind of averaging. You calculate the cumulant consistent with this particular xi, then average the cumulant over all possible xi's. So these two quantities are different. You get a different kind of averaging for the second moment. And there are some well-known results when you look at quenched and annealed averages, but this is the main difference. And then you can, of course, go to higher and higher orders, but this is the main difference. Yeah. Okay. So here are some very well-known results for non-interacting random walkers. You look at the fluctuations in the current for in non-interacting random walkers for the annealed and the quenched, and as David had pointed out, there is a factor of square root 2, and both of them show square root t behavior at all times. But the quenched fluctuations are suppressed by a factor of square root 2. For the symmetric simple exclusion process, you can also derive very similar results, where you see a square root t behavior at all times, but with different prefactors depending on the density. So these sort of results have already been studied in the literature. And then very interesting work by Alberto, Satya, and Gregory on non-interacting RTPs, the model that I'm actually considering. There they were able to show at large times, you get exactly the sort of diffusive behavior, if I just go one slide back, that you see for non-interacting random walkers, but with the prefactor now given by some effective diffusion constant. So RTPs are known to be effectively diffusive at large times. So the current fluctuations are also effectively diffusive at large times, and they were able to show this analytically. So then the question we were focusing on is, can the fluctuations be computed as a function of time at all times and analytically? So we were able to do that, and I'll show you some results. So now here's sort of the crux of the point that I'm going to make today, is that because you have an additional degree of freedom, not just the positions for RTP particles or for any sort of active system, which you have two different fields, you can now perform an even more generalized kind of averaging. You can quench either the positions or the velocities, and you can take all kinds of different averages using this. So I would call it even more different kinds of averaging. So let's see. So you can now, I define another variable where you have not just averaged over positions, but you can also average over magnetization or the initial bias velocity. So then you can now play this game and define all kinds of averages: annealed density, annealed magnetization initial conditions, annealed density, quenched magnetization initial conditions. So you quench the magnetization, keep the positions, keep the orientations fixed, and do the annealed density average. Similarly, you can define quenched density, quenched magnetization. Yeah, that's the question. No. Quenched density, quenched magnetization initial conditions, quenched density, annealed magnetization initial conditions. And we can, very similar to the calculations done by Satya, Alberto, and Gregory, you can calculate all of these quantities explicitly, and I will show you how to do that. So, yeah. Okay, so we follow a very elegant method that was developed recently in these papers, and the way to do that, especially for non-interacting particle systems, is the following. You define, the simplest way to do it is to define something known as an indicator variable, where if some particle is to the right of the origin, this indicator variable takes value 1, otherwise it takes the value 0, and the total number of particles to the right of the origin is just a summation over all of these indicator variables. For a fixed initial realization of the particles and some bias state Mi, you can calculate this quantity. You can just say, okay, you started with some positions of the particles, started with some orientations of these particles, and then you asked, what is the probability that you have q number of particles to the right of the origin at a given time t? So that would be the distribution that we are interested in, and that is simply given by this delta function. Where, the delta function where you sum over all possible occupancies of the particles to the right, and you will just get this quantity. So this is average over histories consistent with an xi, initial positions, and initial orientations. So in order to compute this generating function, suppose I wanted to compute this generating function, e to the minus pq. Q is the flux across the origin, consistent with some xi, consistent with some mi. You will just take this exponential of this quantity summation over indicator variables. Then you make use of a very simple property of this indicator function, that is, because it only takes values plus or minus 1, you can make use of this identity e to the minus pi, which is the indicator variable, is just this on the right hand side, very similar to what you do in the Ising model when you're computing partition function. And what really allows you to do these calculations is that you have independent particles. All the particles are independent, so this quantity that you're calculating, which is the exponential average, can just be written as a product over all possible particles. Right? So when you do that, you just have to compute this average over this indicator function. And now, because you know the Green's functions for these particles, so what is the probability of being on the right for a single particle, you can just calculate this quantity, which is this average over the indicator function, as just an integral over this Green's function. So if you want to calculate what is the probability that a given particle is to the right of the origin, I just calculate the Green's function of a particle being at some position x, starting from some initial position xi at some given time t, and integrate over 0 to infinity, that is to being in the right of the origin at any given time, and this is simply this quantity, and I label it u. But what you will notice here is that I have another variable mi, that is, the Green's function can be different depending on whether you start the position oriented towards the left or start the particle oriented towards the right. And that is labeled by this Green's function label mi, which is the initial magnetization of the particle. And so so we define this quantity u, and the fundamental quantity of interest is this integral, is this generating function that we have written down, which we can write by using this identity. We can write it as this. So again, I'm just following the techniques that were invented recently, but we have now got this extra label of m, which is the initial orientation of the particles. So now let's just compute the propagators in order to use them to calculate the actual flux through the origin. The evolution equations again have been shown before, so I won't go into the details, but simply put, you can calculate the probability of a particle being at a position x at a given time t with, in the state plus or in the state minus, and this is just the advective term, and this is the flipping term. So these two probabilities go into each other, and so this is the Green's function in the Laplace domain, which had been computed before. This is for the case when particles are either in the plus or the minus state symmetrically initialized. But now, if you would like to calculate this for the Green's function for it, either starting in the plus state or either starting in the minus state, it looks a little bit more complicated. But in the Laplace domain, you can actually obtain the exact value. And if you sum this g plus plus g minus, you will get this quantity. So the Green's functions in real space, this is something that Gregory had also shown in his talk yesterday, looks quite complicated. So if you want to do these calculations, it's easier to just work in the Laplace domain because you have to integrate over space, as I showed you. So we can actually just calculate this u function that I was showing in the Laplace domain itself and work with that, because if you do this integral in the Laplace domain, these quantities look relatively easier to work with. So these are the quantities that we can do, and then again, just following these calculations, we can now go through the algebra, and we get some exact results, which I won't go into, but I'll just give you a summary of what we see. So in the small time limit, we actually see that if you initiate particles only in the minus state, the fluctuations actually have a different behavior whether you're annealed or you're quenched. So let me just give one example. In the very, very long time limit, annealed and quenched magnetizations all have the same factor of square root 2 that you would see for any particulate model without this magnetization affecting anything at large time. So you can see, for example, annealed density and quenched density, they're both exactly the same regardless of the magnetization. Why does that happen? Well, because at large enough times the magnetization randomizes, and so the only effect that remains is the fluctuations coming from the initial positions. But at short times, we have some. These results look a little complicated, but I'll show you some graphs where you will be able to see what really the difference is. Okay, so let me go here. One thing that we could do in this particular case, if you start with exactly half, f plus is equal to half, f minus is equal to half, we are able to do one calculation exactly. All of these are fully analytic results. You can actually calculate all the fluctuations, whether it's quenched or annealed, exactly. So these are analytic results at all times, and this is from simulations. So what is the take home from here is that if you look at the fluctuation, so this is the second moment of the second cumulative of the current with time. If you anneal both the positions and the magnetizations, you get a linear behavior in time and a square root t behavior at large times. But if you quench both the positions and the magnetizations, you actually suppress the fluctuations enormously, because now you have much lower fluctuations because both variables are quenched, and you actually get a different power law behavior whether you quench the magnetization or you anneal the magnetization. So that's something quite non-trivial, which we were able to show analytically in this model. Similarly, now we can do simulations and check with different number of particles initiated in the plus and the minus state, and you can show that you have t-squared behavior if you quench both the positions and the velocities, but a linear t behavior if you anneal either one of them, and the square root t behavior for diffusion is recovered in this limit. Okay. So,
okay.
Yes.
On the previous one, you said you had analytical results for
Yes, so these,
zero magnetization, was it?
this is for zero magnetization.
So it's just staggered, like plus
No,
minus?
so these are not, so we have, for example, if you quench them, staggered would also be one of the,
But which one did you take then?
no, we could take any. You can actually take a Poissonian distribution of pluses and minuses on the left-hand side, as long as they don't fluctuate. Just one realization. So staggered will work. Staggered will be this, for example. Quenched and quenched orientations, one possible example is staggered. But what we could do is place spins in using a Poissonian distribution, whether they're plus or minus. You can be plus, plus, minus, 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 plus, something like that. But as long as they don't fluctuate, you will always get this result.
Okay. I
Yeah.
think
So it's in the large n limit that we are taking this. Yeah, yeah, yeah. Yes, please.
Is there a net drift?
No, that's what I'm saying.
Drift
So
is zero.
these results are for no net drift. F plus is equal to half, F
Even
minus
in the quench state, you create exactly equal number of plus
Yes.
and exactly equal number of minus.
on average, yes.
Not
correct.
on average, in each sample.
Yes, in each sample, because you're looking at large n,
Because you
large
are
n,
not averaging over initial state.
we are not averaging over initial alignments, but you can average over initial positions, keeping the alignment fixed.
Okay.
So that is what quenched would be. But you could have quenched annealed, where you have averaged over the initial alignments, but keep the positions quenched, right? And they will have this. In fact, okay, so there's some very interesting point here, which is the averaging of these two quantities. If you anneal the positions, it does not matter whether you anneal or you quench the alignments. Why? Because now you're exchanging the positions. So the alignment doesn't actually matter. So that's why you get exactly the same answer for annealed positions, annealed positions and quenched or annealed magnetization. It doesn't matter because you're randomizing the alignments. But it does matter whether if you quench the positions, whether you anneal or quench the magnetization, that matters. Okay. So this was a summary of what we did for the non-interacting model. So then we decided to look at what is the effect of interactions on such a quantity. To do that, we looked at a simple model that was sort of introduced in the literature a few years ago, which is this active lattice gas model. This model is very simple. It's very similar to the RTP, but now there's a few additional points, which is you look at a lattice model with either plus or minus particles on the lattice, and they are able to diffuse to the left or the right. So they have this diffusion variable as well. Then they have a drift. So the minus particles have a drift to the left, and the plus particles have a drift to the right. There's a hardcore exclusion constraint, and the plus and minus particles can interconvert with some rate gamma. So this is, in some sense, an active version of the VASEP, which is the weakly asymmetric exclusion process, because you have this drift which is scaled by L, and this interconversion which is scaled by L squared. So these L and L squared are there so that you can write down hydrodynamic equations. So this is the model that we consider, and we try to do the same analysis in this case to see what is the effect of the different initial conditions when we're looking at current fluctuations in an interacting active particle model. So you can actually do the coarse graining of this system and show that under diffusive rescaling, similar to what Anupam talked about, where you have some diffusive scaling, you can write down the exact hydrodynamic equations in this model. So you have, sorry, let me go back here. So you define a density rho plus of particles in the plus state. You define a density of particles in the minus state, and you can just write down the evolution equation for this rho plus and rho minus fields, this is basically diffusion. There is some drift term which is coming because of the bias of the plus particles towards the right. There's a effect of the exclusion, which is this 1 minus rho term. This is very similar to the hydrodynamics of the ASEP or the VASEP. And then there's this term coming from the interconversion between the rho plus and rho minus. Similarly, you can write down the equations for rho minus in the exact same way, where now you have this sign is flipped because now this is biased towards the left, But this exclusion term is 1 minus rho because either the plus or the minus can lead to exclusion. And so this is the coupled hydrodynamic equations for this lattice model that I was talking about. But now if you want to compute the fluctuations of the number of particles to the right, the hydrodynamic equation will tell you how average number of particles to the right. But we want to compute the fluctuations of this quantity. What is the flux through the origin? For that, we need to write down fluctuating hydrodynamics equations. So you take the same hydrodynamic equations, and now you add fluctuations to this. The fluctuations had been conjectured in this recent paper by a very elegant mapping to the ABC model. I won't go into that in detail, but once you have the full fluctuating hydrodynamic equations, you can now compute quantities like the flux across the origin, how many particles have gone across the origin at a given time t, and what are the statistics of that particular quantity. So just one point to note is that because the drift conserves density, we have this is a conservative noise. These two terms are conservative noise, but because the flipping term does not conserve the density, this is a non-conservative noise. So this model has both conservative and non-conservative noise, but the mapping to the ABC model actually allows you to write down what the correlations between these noise variables are. So once you have these equations, we can do the standard formulation of macroscopic fluctuation theory. I won't go into the equations there, but we can then compute using these fluctuating hydrodynamics equations what the second moment and the second cumulant of this quantity Q, which is the flux across the origin, will be. So let me just show you one point here. You can actually write down scaled hydrodynamic equations for this model, where you can write down density and magnetization, very similar to the two quantities that I was considering for the non-interacting case, where you have a density variable, which is the total number of particles in space, and you have magnetization, which is the difference between the rho plus and rho minus fields. And if you look at the density variable, you get this very nice conservative equation because the density is conserved. But if you look at the magnetization variable, you'd get it is not conserved. You have this extra term here, and you can actually perform a second rescaling and write everything in terms of this Peclet number. And this fluctuating hydrodynamics equations take a particularly simple form when you do such a scaling. Yeah. So the point is, let me just go back one step. If you have fluctuating hydrodynamics equations, you can now compute dynamical correlations using that. And you can also look at, for example, the linear stability of these equations and compute a phase diagram. So that has already been done in some recent work. And here I'm just plotting the correlation length that you can compute using the fluctuating hydrodynamics, and you can compute the linear stability of those hydrodynamic equations. And you see that with Peclet, so let me just go back. Peclet number is basically this quantifying the activity in the system. Lambda is the bias. So it's roughly the ratio of bias motion to diffusive motion. So that's usually known as the Peclet number. As you increase the activity in the system at some critical density 3/4, you get instability, and you basically get a phase transition, which people somehow refer to it as the MIPS phase transition, but there is some debate about that. But the correlation length diverges at this point. So now within this model, the question becomes, what would be the current fluctuations if I was to look at this model and then just look at how the activity and the interplay of interactions drives current fluctuations in such a model? That would be something that we will be able to uncover using these fluctuating hydrodynamics equations. So we did that calculation by actually starting with exactly the same initial conditions that I did for the non-interacting case, step initial condition with a step magnetization initial condition as well, and just compute this quantity, how many particles are to the right. So that is starting with some step initial condition, what is the number of particles that have crossed from the left to the right. This is this quantity Q that we are interested in computing. And we were not able to do the exact calculation for general, so let me just go back. For general step initial condition, this became quite a hard problem. We were not able to solve it analytically. So we took one special case where we are able to do it, we are able to solve it for flat initial conditions. So the density on the left and the density of the right is the same. So using flat initial conditions, we can actually solve these hydrodynamic equations exactly and get the following result. So I'll just tell you the results and won't go into the details. So in the small time limit, we see that there's some square root t behavior emerging. In fact, this is exactly the same answer that you would get in the symmetric simple exclusion process. Because in the symmetric simple exclusion process, for short times, you're only seeing the bias, and the effect of the flipping has not yet come into play. But at very, very large times, we are able to show that you again get this square root t behavior, but with a modified prefactor, which has both the effects of the Peclet number as well as the effects of activity, so of the density as well. And it also has this correlation length that diverges, also appears in the current fluctuations. So this was exactly shown before, that the correlation length diverges at some point, which is given by this point. And so this is what we see. So what happens in the case where, so let me just go back one step. So this is what we see in general. But to map to the non-interacting case, where we were just looking at velocities either going to the right or the left with no diffusion, what you can do is take the diffusion going to zero limit. So it's a zero diffusive case. We actually see that we get the square root t behavior and these match exactly with the results by Satya, Alberto, and Gregory for the non-interacting case. But when you go to the very, very short time, we see this t squared behavior emerging, which tells us that you actually, when you're looking at this interacting lattice gas, we're actually looking at both the quenched positions and magnetizations, and it actually matches with the non-interacting calculations with quenching both the positions and the magnetizations. So then I'll just show you some results from simulations. This is the match with the hydrodynamic equations for this interacting lattice gas model. You start with some step initial profile, and you just run the hydrodynamic equations, and the simulations exactly match with the hydrodynamics. And using this, so the rho and the m fields exactly match. And using this, you can actually also do the fluctuating hydrodynamics. I won't go into that. Here is the match. Yes, please. Yes. Yeah, short time with respect to gamma inverse is one. Yes.
Like also with respect to the gap divided by the velocity.
Yeah, that's a good point. So there is a time scale which comes from this rho. So this reproduces the single particle behavior in the low density limit.
Yeah. No, the very short time is like a single particle, t going to zero limit.
T going to zero limit here.
It's like a single particle.
It's like a single particle if you are looking at the rho going to zero.
Yeah.
Both of them. Rho going to zero is the non-interacting case. But if rho is not zero, then you stick the time scale.
But that also will change this t, right? I mean,
that will change the t.
When you're saying t going to zero, with respect to what?
Yeah, so the t going to zero with respect to gamma inverse.
Only with respect to gamma inverse,
Yes.
not with respect to rho v.
Not with respect to rho v, not in these two formulae.
Okay.
Yeah. So this is the match with the short time asymptotics. When we look at the current fluctuations for very, very short times. But unfortunately, in this lattice model, we weren't able to go to very large times to match what we would see as this is a square root t behavior at very short times. We would see some increasing fluctuations, but we were not able to see because of lattice effects, the finite size of the lattice. But here is the theoretical prediction. What you would see is that at very short times, you will see the current fluctuations that you see in this symmetric. Yeah, I'm almost done. In the symmetric simple exclusion process, where you get this square root t behavior initially, and this prefactor is exactly given by the symmetric simple exclusion process. Then activity drives these very large current fluctuations, and then you end up seeing some current fluctuations which are the square root t behavior. But if I was to match with the non-interacting case, you would see the square root t of the non-interacting case is larger than the interacting case. So the current fluctuations are actually suppressed with respect to the non-interacting case. And then this you can actually see by changing the density. So if you change the density, you start with some average density of 0.1. initially, because there's a particle hole symmetry in the problem, you will see that 0.9 and 0.1 give you the same current fluctuations. But at large times, you will see that these two will not be the same. So you get, initially you get some square root t behavior, but then the current fluctuations will deviate from that. And then finally, we can also look at what happens as you get closer and closer to the critical point. In the critical point, which is basically, so let me just go back to the original picture. Yeah. So here the critical point happens at density 3/4 and Peclet number of 4. So we can either go in this direction, start with single density and increase the Peclet number until you get to this point, or you can start with this Peclet number 4 and increase the density until you get to this point, and see what happens to the current fluctuations as you get to this critical point. It turns out that the current fluctuations actually diverge as you get there. So let me just show you that. So these are our theoretical results, what we expect at large times. As you increase the Peclet number and go closer and closer to the critical point, the current fluctuations diverge. And we would like to see what happens as you decrease the diffusion constant as well. So because in order to connect it with the non-interacting case, where we did not have a diffusion, it was just simply flipping, so no diffusion constant. So we can actually decrease the diffusion constant and go all the way down and see that the t-squared behavior is reproduced when we decrease the diffusion constant, and you have a square root t behavior emerging at late times. So with that, I'd like to conclude. We analytically computed current fluctuations across the origin for both non-interacting RTPs as well as an interacting active lattice gas, which we can show in the limit of rho going to 0 becomes a non-interacting RTP problem. We were able to show that the asymmetry in the initial bias directions can lead to very different power law behaviors in the current fluctuations, which is sort of a strange effect that sort of warrants more investigation. Cumulants of the time integrated current for the interacting active lattice gas model match with the non-interacting case at low densities, which is what I showed by decreasing the diffusion constant and taking the density going to 0 limit. And yeah, so it would be interesting to basically study these sort of generalized disorder averages where you can quench multiple fields and allow for annealing of other fields to see what kind of different fluctuating behaviors you can get from other models. There are other models, for example, you have coupled densities with magnetization fields in sedimenting models, which we are presently studying, where very similar hydrodynamic equations appear. And so we would expect the effects of quenching one of the fields, either quenching the slopes or quenching the density, to have very different effects on the current fluctuations. So this is something that we are actively studying, and that, thank you. I'll take some questions. Yeah.
So if I can just get in first.
Yes, please.
So I'm used to the idea of the quenched and annealed cases, but you had a particularly nice way of illustrating it with the expanding the generating function.
Yes, let me go
right
there.
at the beginning.
Yes. So this is the usual way of,
This is the,
yes, let me go here, yeah.
So there's just one term there that's different.
So
that one.
Yeah, so this and higher order terms. Yeah, so what you do here is actually compute the cumulant fixing xi. So if I just do this expansion, so for every xi, I compute the cumulant and then average over the cumulants. Whereas here, I compute the moments and then average the moments and then compute the cumulants.
No, absolutely. I just was trying to figure out in my head the difference between those two terms in particular.
Yeah, so it's where the overbar is. So the overbar is here, whereas the overbar is here over the full cumulant. Oops, sorry. Oops. Yeah. Sorry.
Herbert.
I have one question. I mean, if you look at, for instance, at the TARCEP,
yes.
I mean, then you see that this integrated current, I mean, they scale like t to the 1/3.
Yes.
And so somehow I was hoping that somewhere on your slide, I mean, this would appear. Could you explain why this exponent does not appear?
Because we are looking at the weakly asymmetric limit where hydrodynamics can work. So this is not, in the TARCEP, you cannot write those hydrodynamic equations. Yeah, so that's the reason that the 1/3 is there.
So you're always looking at the weakly asymmetric.
Yes, with this, again, so let me just go back. This is a very good question. We always look at the lambda by L. So that's the weak asymmetry.
So you're saying it would be a difference. You'd get different results.
Yes, you would get different results if you look at task. Exactly, yeah. Yes, please. Yeah.
Sat here. Oh, no, sorry. No, please.
Sorry,
Yes, please.
just one related question. Suppose you look at the strongly asymmetric limit numerically.
Yeah.
What do you get? Like if you do just microscopic numerics, doesn't with these dynamical rules that should be doable, right? So
That should be doable, but
so
as,
what happens
we
if
have
you-
not checked that. The reason being that we'll probably see the 1/3 as Herbert is pointing out, but we won't see the effect of activity because somehow we are not able to go to those lattice sizes where we'll see the effect of activity. If I was to continue this line, this is square root t, which is the SSEP result, then the activity will give you some result here, and then the square root t will come out here.
Okay.
We are not able to go to those lattice sizes, but if you were to do the lattice sizes you're talking about, we will definitely see the square root, sorry, 1/3
1/3,
behavior,
okay.
and then we don't know what happens after that. But yeah, numerically we are limited,
Okay.
unfortunately. Yes.
Thanks.
Yeah, hi. So, in fact, in the Brownian case, non-interacting Brownian case, so the David and Gregory, we had also studied the current up to time t, but as a process in time t. And there it turns out that this is a multivariate Poisson process, for example.
Yeah.
So you can calculate 2.2-time correlation
Yes,
function and so
that's-
on.
yeah.
Can you do that for the RTP?
I think we should be able to, but we haven't tried it. But that's a really good point, yeah. And there you can see fractional Brownian motion and so on.
Nice.
Up here, yeah. Yes, please.
When you go close to the critical point,
Yes.
and you're doing the analysis still based on the fluctuating
Absolutely
hydrodynamics,
correct, yes.
and you know that close
We
to
expect that
is
the
there-
fluctuating hydrodynamics should fail somewhere here, yeah.
Right. So how reliable is your result then? near
That's a good question. We have not tested how reliable it is, but yes, it should fail. Beyond this point, it definitely fails. How good it is as you get beyond this point, the fluctuating hydrodynamics doesn't work. Yeah, that's up for debate. I know that many people are studying it, but as far as we know, that fluctuating hydrodynamics doesn't work on that point. Yeah, yeah. But you're right. Getting close to the critical point, there should be some effects of the correlation length. The infinite correlation length should make the fluctuating hydrodynamics not work. So we are not sure. We see current fluctuation diverging there. So yeah, we might have to go to higher order effects. Yeah.
So I had two questions.
Yes.
So one was like when you use fluctuating hydrodynamics to compute the cumulants. I mean, so do you sort of do just linearized hydrodynamics, or I guess that's
No,
what-
yeah. So the way to do it would be write down an action, bias the cumulant generating function, bias the action with the
Okay.
cumulant generating function e to the lambda q,
Right. Okay.
then calculate the solutions, and then the usual macroscopic
Okay, fine,
fluctuations.
yeah. So the other question was like, did you look at the profiles, like the density profiles, both in the non-interacting and interacting case, and is there some signature of activity that you see there? And like if you just look at the evolution of the density profiles.
Okay, I understand. So let me just here like this. We haven't checked that. That would be interesting. Yeah, I mean we have equations that govern the. We have the non.
Both in the non-interacting and interacting cases, I guess you can explicitly find it.
Yes, we can write down the hydrodynamics for
Yeah.
the
So there, do
non-interacting.
you? I mean, you still see some signatures of activity, or like the non-interacting case. Does it quickly go to the diffusive solution? I mean.
I'm not sure. I'm not sure. Yeah. Yes.
Can you eliminate the spin field, let's say, from the fluctuating hydrodynamics, just to obtain the fluctuating hydrodynamics completely in terms of rho?
Not in the interacting case at least, because they're, sorry, let me go back. They're coupled. So you cannot simply eliminate M.
But maybe a higher order in time with memory it will be.
Yeah, I do not know the answer to that. Maybe you can, but it's not simple. Yeah.
No, but is that bad? But the fluctuating hydrodynamics with memory, maybe.
Are there any more questions out there?
Yes, please.
You made a comment that in the phase diagram that inside this fluctuating hydrodynamics doesn't work. I mean, what do you mean? I mean, if the fluctuation hydrodynamic doesn't work inside, then the hydrodynamics is useless, right? Because in the sense that the noise is of 1 by square root of L, right?
1 by square root L, yeah.
So in the limit L going to infinity, if the noiseless hydrodynamics cannot give the correct answer, then one should just throw away that result, right? So what do you mean by that this fluctuating hydrodynamics doesn't work inside?
So it gives you the phase separated, it gives you the phase separation.
It will not give you a homogeneous state, but that's, even if you put a noise, that's a stable state, right? I mean, noise cannot kill that phase separated state, no?
Yes, you're right. But the question then becomes, suppose you have a phase let me just go here. So suppose you have phase separation, here it basically becomes flat, right? Suppose you have phase separation, then the question is, does the noise actually have the same correlations that you would put in here?
No.
Yeah. That I do not know. As far as I know, from our simulations,
your analysis may not go through. I mean, analysis will be probably more complicated than the homogeneous state. But it's not that the noiseless, noisy hydrodynamics doesn't work, no? I mean, that's...
So noiseless equations will predict even the phase separation. That we have checked.
Yeah, but even the noisy hydrodynamics should retain those phase separated state, right? I mean, otherwise you should actually throw, otherwise there is no meaning of the phase separation given by the noiseless dynamics, right? Even if the little bit of noise destroys that, I mean, that was the point of writing down the hydrodynamics.
I understand this point, this part will give you the right phase separation. I'm saying this part, no, I'm not sure if the correlations of this will
what
be
I'm saying is that that part is of order 1 by square root of L, right? If large L, if that part destroys the, whatever the result of the noiseless hydrodynamics, then there's no point writing down this noiseless hydrodynamics anyway, right? I guess you write down the noiseless hydrodynamics because that part cannot kill your whatever the prediction of the...
I understand your point, yeah,
right?
That remains to be seen. I do not know the answer
right?
to that. Yeah.
I guess it will probably still stay, whatever the state, I don't know, I mean...
I think you are checking that, right? So I don't know.
The phase separate state. One is a bulk phase like a liquid, and another is a gas. And each state locally is in equilibrium. So you can, the noiseless hydrodynamics would work inside each smaller pure phases.
Possibly
And
true,
that
yeah.
should-
Okay, thanks.
Okay, we're about done? I think so. Okay, so let's thank both our speakers for this afternoon. And I guess we reconvene at 4:30.
See, because if noise kills the hydrodynamics, then there's no point writing down the hydrodynamics, right?
No, I understand that, but it's